In calculus, we've gotten really good at lines and curves. But what about the real world? I mean, how do we use math to describe something like the surface of a sphere, or the curve of a vase, or even a crazy complex 3D model?
So that's the big question, right? A simple circle, easy. We all know x squared plus y squared equals r squared. But how do you write an equation for, well, almost any surface you can possibly imagine? The answer, it turns out, is both super elegant and incredibly powerful. Okay, so to get this, I want you to hold a picture in your mind. Just imagine a perfectly flat, infinitely stretchy sheet of, like, digital graph paper. The whole idea behind parametric surfaces is that we're going to take this sheet and we're going to tell every single point on it exactly where to go in 3D space to build our final shape. We're going to warp it, stretch it, maybe even fold it.
All right, so let's take that analogy of a digital sheet and turn it into a real, formal mathematical concept.
So here it is, the formal definition. A parametric surface is defined by a vector function that depends on not one, but two independent parameters. We usually call them u and v. And these two parameters, they're the secret sauce. They're what unlocks the ability to describe a whole surface instead of just a single line.
This slide really nails the concept. Think of the pair UV as an address on our flat sheet of graph paper. You give me a UV address, the function crunches the numbers, and it spits out an XYZ coordinate in 3D space. As you let UV wander all over its domain, you're basically painting the entire surface into existence, point by point.
Okay, so let's keep going and see how this all builds into a formal equation. If that u, v pair is the address, then the vector function itself, well, that's the blueprint. It's got all the instructions for building our 3D shape. And this comparison is absolutely key. You're probably familiar with space curves, r of t, right? They use one parameter, t, to trace out a path, kind of like a single thread moving through space. Well, a parametric surface, r of uv, adds that second parameter. This lets us move in two independent directions, basically weaving that single thread into a whole sheet.
But of course, just describing a surface isn't enough. I mean, this is calculus. We need tools to analyze it, to find things like slopes, orientation, and eventually area. And that's where, you guessed it, derivatives come roaring back into the picture.
So how do we do that? We analyze our surface by looking at what are called grid curves. Imagine for a second you hold v totally constant and only let u change. What you get is a curve traced across the surface. The partial derivative with respect to u, which we call ru, is just a vector that's tangent to that curve. And you can do the exact same thing for rv. Together, these two tangent vectors, they define a tiny little tangent plane on the surface at any point. And from them, we can find the super important normal vector.
And here's the recipe for it. It's actually pretty straightforward. First, you find your tangent vectors by taking the partial derivatives, ru and rv. Then, you take their cross product. And if you remember from vector calc, the cross product of two vectors gives you a third vector that's perpendicular to both of them. In our case, that means it's normal, or perpendicular to the surface itself. Boom!
Okay, theory is great, but the best way to really get this is to see it in action. So let's walk through a couple of classic examples. All right, for our first example, we're going to work backwards. We're given a parametric equation, and our job is to figure out what familiar shape it actually describes. Our vector components are x equals 2 cosine u, y equals v, and z equals 2 sine u.
So the game here is to eliminate the parameters u and v. And when you see a cosine and a sine paired up in the x and z components like that, that should be a huge hint, a big flashing light. If we square x and z and then add them together, that classic trig identity, cos squared plus sine squared equals 1, makes the u parameter just vanish. What we're left with is x squared plus z squared equals 4. And since y is just v, it can be any value it wants. Well, what's that? That's the equation for a cylinder of radius 2, centered right on the y-axis. See? Not so bad.
Okay, example number 2. Let's use that procedure we just learned. We need to find the normal vector to this paraboloid, given by r of uv, at this specific point in space, 1, 2, 5. First things first, we need those partial derivatives. The derivative with respect to u gives us ru, and the derivative with respect to v gives us rv. Super simple. Now we need the parameter values that correspond to our point 1, 2, 5. Well, since x equals u and y equals v, our parameters are just u1 and v2. Now we plug those values into our derivative formulas to find the specific tangent vectors at that point. So our u becomes 1, 0, 2, and our v becomes 0, 1, 4. And listen up, because I cannot stress this enough. This is a super common mistake. The derivatives are functions of u and v. You have to plug in the parameter values u equals 1 and v equals 2, not the final x, y, and z coordinates of the point. Remember our analogy? The parameters are the address on the flat sheet, and that's what our calculus tools are designed to work with.
Okay, now for the final step, the cross product. We set up our little determinant with I, j, k, and our two tangent vectors. We calculate it out, and what we get is our normal vector, n equals -2, -4, 1. And that vector right there is perfectly perpendicular to the paraboloid at the point 1, 2, 5. Done.
So, okay, we can describe surfaces and we can find normal vectors. But what's the big picture here? Why did we just spend all this time calculating tangent vectors and their cross product? Well, there's a deeper secret hiding here, and it has everything to do with area.
Let's just take a quick peek at a result for a sphere, which uses parameters phi and theta instead of u and v. If you go through this whole process for a sphere and calculate the magnitude of the normal vector, you end up with this term, a squared times sine of phi. Now, for those of you who've already battled through integration in spherical coordinates, does that term look a little familiar? It should.
And here it is, the big reveal. The magnitude of that normal vector, the length of RU cross RV, that is the surface area element. Think of it like the Jacobian, but for surfaces. Let's go all the way back to our original analogy. This value is a correction factor. It's a fudge factor that tells us exactly how much that tiny little square on our original flat graph paper got stretched or maybe squished when we warped it into our final 3D surface.
And this isn't just some neat mathematical party trick. This stretch factor is the absolute key. It's the essential ingredient that unlocks our ability to do calculus on curved surfaces. It's the bridge that takes us from just describing shapes to actually analyzing them in a meaningful way.
And that leads us to the final tantalizing question. We've just found the formula for the area of one infinitesimally small patch on a surface. So, what do you think happens when we use an integral to add up the areas of all of those little patches? Well, that, my friends, is the gateway to surface integrals, and that's where things get really interesting.